Okay, so now I'm going to first do another enter and exit range worked example when both the sensor and the target are moving. Then we're going to look at an implementation. We're going to start looking at implementation of this detection and undetection events, as well as the enter and exit range stuff. So to that end, we have a number of different classes. And the way that I like to do the sensors is have these sensors and mediators, and then this referee that's going to adjudicate the enter and exit range events. To that end, since there are going to be a number of different classes that will implement different rules for scheduling the detections, because there is some constant or common capabilities, we're going to have an abstract sensor that we're going to define, and then have some concrete subclasses. So for this, we're just going to look at the cookie cutter and that constant time. So just to show that there are going to be two different ones. Then once we have that in hand, then we can look at the simplest referee. Again, by simplest, we're taking the bare minimum for this, and we'll, as we will discover, as with the simplest mover, there was a limitation to carrying it further. So we needed to kind of up the game a little bit. And of course, I made you be the ones to up the game, but that's my prerogative. And then for the idea of modeling this time to detection is done by a pair. So the simplest cookie cutter sensor pairs with the simplest cookie cutter mediator, and the simplest constant time sensor will be paired with the simplest constant time mediator. And all of that is because, as we went through before, that the sensor itself shouldn't be responsible for scheduling these detections. So it's this mediator that kind of represents the process of detecting a target once it's gotten into range. Okay, so, but now let's have I want to do a worked example, so you have something to see where both the sensor and the target are moving. And again, we're going to talk about time zero, because every time you have an event, it's because we're calculating the delays, it might as well be at time zero. So just having the extra time introduces just a little bit more noise into our calculations. So just to make it simple, we'll assume we're at time zero, with the understanding that typically this is going to be done at some positive time, and the calculation that we come up with to schedule the enter range is going to be a delay that we put in at the scheduling. Okay, so here we're going to start at minus 50/50 and move to a destination of 130 at a speed of 20. Okay, so that's our mover. Our sensor is going to be located at 130. It has a range of 25. And then at the same time, it starts moving to destination minus 10, 140 at a speed of 30. Okay, so when the sensor is nice and stationary, then we can kind of draw a little picture to kind of see things. So when they're both moving, it can be a little bit more unclear. So the questions that we have are, what are the two equations of motion for the mover and the sensor? When, if any, does the mover enter the range or exit the range? And then finally, if the sensor's time to detect is, say, 0.05, then when does the sensor actually detect the mover? Okay, so remember, this is our canonical sequence. So what we're doing is we're first of all calculating the enter and exit range, again, using this equation. And then we're given all that, we're going to compute the time to detection from enter range to detection. Okay, so first the mover's equation of motion. We look at the destination minus its initial location. So that's 130 minus a minus 50/50. So that comes down to 80/80. And so the norm of that is going to be the square root of the sum of the squares, which turns out to be 80√2. The velocity is going to be the speed times the vector turned into a unit vector. Okay, so that would be, so here's the 80/80. The speed is 20. And then we divide by the norm. And so we get 20/√2, 20/√2. And again, remember that you always want to carry your calculations to as many decimal places as possible. And so we don't want to round off here. If you round off too early, then the round off errors tend to accumulate. So our equation of motion for the target is minus 50/50 plus time times 20/√2, 20/√2. Okay, now let's look at the sensor. We apply exactly the same logic. So its destination was 130, its starting location minus 10, 140. The difference of the two is minus 110, 110. So again, we have our square root of the sums of the squares, and it's 10√242. Again, I just kind of took the 100 out. I could have taken an additional 11 out, but I'll leave that for the interested or disinterested student. All right, let's look at the velocity now. So we take the difference of the vector, divide by our norm, and that gives us our unit vector, and we multiplied by the speed. The speed was 30. And so now our velocity vector for the sensor is minus 330/√242 and 330/√242. So this is the equation of motion for the sensor. Again, it's initial location plus the elapsed time times its velocity. Okay, so now that we have the two equations of motion, we can now determine the target's motion in the sensor's coordinates. So that's what we need to do in order to bring everything into a situation where the sensor is stationary at the origin. So the relative location is the difference between their starting locations. So that's the target minus the sensor. So that means in the sensor's coordinate system, the target is at minus 150/20. The velocity similar is the difference of the velocities. So that's just these two things. And again, we want to carry it out as much as possible. So there's no, in this case, there's really no reason to simplify this any further until the very end where we want to find a number. Okay, so now we have everything we need for determining the enter and exit range. So what are the elements we need? We have the norm of the target's location squared. Again, so we use this, the relative one, not this one, not this one. Again, the relative velocity squared. So we square all that, and it turns out that we actually get 1300. That came out to an even thing. It usually doesn't, but. And then when we look at the inner product, again, the inner product would be the x. So it'd be 150 times this first element plus 20 times the second element here. So minus 150 times this, 20 times that. And so again, we get this, which is likewise, as before, a negative value. So that tends to indicate that the target is heading toward the sensor. Now, we still don't know if it's going to actually hit it or not, but we do know that we're going to have, we are going to have two roots, two real roots. No, I'm sorry, I take that back. We don't know, we don't know that yet. We need to do this computation. So this is the expression under the radical. So it's the velocity, norm of the velocity squared, the difference between the square of the range and the square of the relative location, and then we add in the inner product squared. So that would be, again, 1300, that was the velocity squared. The range was 25, so 25 squared is 625. The norm of the relative location was 22,900. And then the the square of the inner product. Remember, we computed the inner product, and when all that settles out, we get this value. So now we know that there will be two roots. And in fact, what we do know actually, what we do know from the negative value of this is that if we have real roots, they will both be positive. Is that? No, we don't necessarily know that yet. In this case, there are going to be positive, well, forget I said that. Okay, so now we can compute the two elements. Let's do the second one first. That's the square root of this value here, divided by the norm of the relative velocity squared, and now we can kind of now we can finally approximate it. And then the first term, which is minus this, so we have minus, should be a minus here, and that's approximately 4 point something. And so our time to enter the range is going to be 4.1882 minus 0.6378, so it's this value, and then we can compute the time to exit the range from now to be 4.8 something. Okay, so that's the that's how to do the calculations when they're both moving. And as you can see, it's fairly involved, but it's not really rocket science at all. Okay, so now let's look at implementing the enter and exit range events. Okay, as I said, we're going to start with the simplest sensor objects, and we're going to have an abstract superclass and then a subclasses, which are going to simply add parameters. So the role of the sensor objects is simply severalfold. One is to maintain a list of the contacts, that is the targets that it's detected, to schedule the detection and undetection events, and then finally to have parameters that will be used ultimately by the mediators. In order to do the enter and exit range events, we're going to have our simplest referee is just going to deal with one sensor and one target, and what it's going to do is it's going to listen to both of the sensor and the target for their enter, and it will schedule the enter range and exit range based on the quadratic equation solution. That is everything that we just did, we're going to do on the computer, and then use what we've learned from that to schedule the enter and exit range events. So that's what we're after here. So the basic idea is that the sensor objects, they have detection and undetection events. The sensors maintain a list. Well, it's going to actually be a set of detected targets. So whenever there's a detection, you'll add the target. Whenever there's an undetection, you'll remove the target. Now, because we've talked about how sensors move, we have a choice here. We can either redo all of the stuff that we had for a mover in the sensor, or what we're going to do instead, which is based upon the programming virtue of laziness, we are going to delegate its movement to a mover object. In other words, the sensor is going to move around, but it's going to move around according to a mover object that it's going to be conceptually sitting on top of. Otherwise, sensors are going to simply have parameters used by mediators. So other than that, sensors are going to be remarkably passive. They're going to be hearing their detections from the mediators, and they're just going to be responding accordingly. Now, the next object is going to be our referee. And so what its job is to listen to a mover and a sensor, that is a target and a sensor, and it's going to listen to their start, move, and end move events. And when it hears those, it's going to schedule the enter range and exit range events. And then, so first I'll kind of go through that. Okay, now where does that come from? If we look at our canonical example here, so when a target starts its move, then the referee is going to hear that, and then in this case, it would schedule the enter range. But if it's inside, it would schedule the enter exit range. And if it was outside, it would kind of do something else. And then because it could be, look at this situation here. Supposing we have a sensor that just kind of moving like this. And we have a target that's kind of moving like this. And but it's moving so fast that if it kept moving, the sensor would kind of miss it. But for some reason, it decides to stop here. In other words, it has an end move event here. And because it did that, in other words, when you do this calculation from the start move, then there would be no intersection. Why? Because in this case, the sensor is moving, the target's moving so fast that the sensor is not going to reach it. But then sometime later, though, instead of continuing on that, it decides to end its move right here. And in that case, there will be a detection. So what that means, therefore, is that the referee is going to have to listen to both start move and end move events for both the sensor and the target, and then schedule the enter and exit range events. So let's see here. Let me share the whole. Okay, so now let's look at implementing this. Okay, the first thing is this abstract sensor, and I call it the simplest abstract sensor because it is the simplest version of this. It is an abstract class. So we have seen abstract classes before, but this is, I think, the first time we've actually perhaps written one. Well, by we, I mean me. Okay, so the simplest abstract, it's a sim entity base, but it's an abstract class. So here's what it has. It has a simplest mover, which is going to be giving it actually all we need for the calculations are the location and the velocity of the sensor. And it's going to get that from the mover. This is actually something called delegation. The sensor is going to delegate its location and velocity to this mover guy. And then it's going to have a maximum range. That's what we were calling R. Now its state it has one state variable, and that is going to be the contacts. See, let's go back to that. Okay, yeah, let me, before I get into that, let's at least kind of walk through it. Okay, again, its parameters are going to be a simplest mover used for location and velocity, a maximum range, and so targets outside of this cannot be detected. It has a single state variable, I'm going to call contacts. It's going to be a set that contains the detected targets. And it has two delegated implicit states. So the current location, it's going to get from its simplest mover, and its velocity, it's going to get from its simplest mover. So all of that is going to be happening. So here's how the event graph looks on this. So here's our simplest abstract sensor. Notice that it's written in italics, which indicates it should, well, an indicator that it's abstract. Okay, so here's its run event. It has one state variable, the context, so it just clears it out after that's the only state transition. So here are detection and undetection events. And those are very simple. So when there's a detection, we simply add the argument. The argument is going to be the target which has been detected. It's going to simply add it to the context. And when there's an undetection, we're going to remove it from the context. Very straightforward. So now, as far as the movement goes, looking down the line, the referee is going to need to know when the sensor has started its move or ended its move. So to that end, the abstract sensor is going to hear a start move from its mover and schedule another event. Now it needs, the referee needs to know whether a sensor or a target has actually started moving. So I'm going to call it start sensor move, and that's going to indicate that it was the sensor that moved, not the target. And likewise, the end move, which is heard from the simplest mover, so that will schedule an end sensor move. Okay, so this is the event graph that we are going to be implementing here. Okay, so we've already started it. Now, as usual, we have a zero argument constructor and a master constructor. Since we have a container, in this case, a set, which is a state variable, the pattern that we've been following as much as possible is to instantiate that container in the zero argument constructor. So we do that. And so the master constructor will call this to make sure that the context set is always instantiated. We're going to make it a hash set because we don't really care about the order. If we cared about the order, we could make it if we wanted to care about the order that we detected things in, we could make it a linked hash set. And if somehow there was some other means of sorting them, we could even make it a sorted set. And all of that is extra complexity. And since we're in the simplest realm, we're not going to worry about that. Okay, so we just need to make sure that we give it a mover. This is going to be, the mover is going to be what determines its location and velocity of the sensor and the maximum range. So reset is just going to clear, again, just as, so clear the contacts. Okay, and run is just going to fire a property change because we don't have anything going there. So again, detection event. So the argument is going to be a simplest mover. So it's just going to detect these targets. And again, we get the old value, add it, fire property change. Now, just for, this is actually just mostly for debugging purposes and just some other things. We're going to sort of add another sort of phantom state called detection. And we're just going to fire that property change and pass the target that we've detected. That's so that we can, especially for debugging, we can say, okay, we've actually detected this target here. Undetection works exactly the same way. We get the old context, we remove the target from the context, and then we fire the property change, and then we'll fire an additional property change called undetection. Just notice the difference in spelling. So the undetection event has a capital U, the undetection phantom state has all lowercase. Okay, so here's it's going to hear from the mover, the start move, and then schedule the start sensor move. And likewise, it's going to hear the end move from its mover and schedule the end sensor move with a 0 delay. Okay, now here's where we use the delegation. And unfortunately, Java doesn't directly support delegation. There are some languages that do, but here we just have to kind of do it by hand. It would be nice if the language had some way of us saying, oh, we're going to have a get velocity method, but get it from this guy. Okay, but instead we're just going to return the mover, the mover's get velocity, and just as an extra, if somehow the mover just happens to be null, we're gonna return a not a number. Actually, probably in thinking about it, it might, well, if it's null, then that means that we've kind of missed something, but we want to at least pick that up. Likewise, the current location. Our mover's current location is going to be where we are. So basically, it's like if somebody says to the sensor, where are you? The sensor says, I'm with stupid. Okay, so, okay, getter for the mover. Now here's one thing that we can do with when we set the mover. Okay, and notice that we're setting the, we set the mover in the master constructor. And when we do, we're going to add this sensor as a sim event listener to the mover so that when we hear it start move and end move events, we can schedule our own move events. Okay, so that's the abstract sensor. Now, our first subclass of that, we're going to call the simplest cookie cutter sensor. So remember, a cookie cutter sensor has the time between enter range and exit range as 0. It's going to be a concrete subclass, and so just looking at the simplest abstract sensor, I should have put this in italics, but the simplest cookie cutter sensor is going to concrete subclass. It has no additional parameters, no additional events. Okay, but it's concrete. So let's see what that looks like. Simplest cookie cutter sensor, we extend simplest abstract sensor. And then all we have are constructors. See, because the all the cookie cutter sensor needs is the range, doesn't have anything additional. So, and there are a variety of ways of doing this. There are competing criteria. If you remember, when we have more than one constructor, the ideal is to only have one constructor that actually calls super, and every other one calls this. That's what I've chosen to do here. The other thing is that now we could simply have passed the mover and the max speed to the super. So an alternative would have been to call super and pass these to it instead of having to call the setters. Which way is best? Again, they're competing, conflicting criteria, so just sort of pick your poison. The important thing is to make sure that all of the correct parameters get in there. Okay, so now we have at least one concrete sensor. And let's see, yeah, no, so the next one is the constant time. So again, it too is a concrete subclass of simplest abstract sensor. And the idea is that we have a fix that is constant time between the enter range and the detection. And so all it does is it adds a parameter, and we're going to call that time to detect. And we're not going to have any additional events. And so let's take a look at what that looks like. The simplest constant time sensor. Again, we extend simplest abstract sensor, but we add a single value, time to detect. And now for this one, I've chosen to do it the other way, to just call super. Now look, our master constructor now, we need the parameters for the superclass, the mover and the max range, and then we need a third parameter, which is, in this case, calling time to detect. So this is the other way to do the constructors. So I call super with the mover and the max range, and then I set my time to detect. That's the one additional parameter. So all I'm adding is the time to detect, and it's a parameter, so it's private. It has a setter and a getter. I have a getter and then the setter. And the thing is, the time to detect, it could be 0. If I have a constant time sensor with a time to detect of 0, then it's the same as a cookie cutter. Is that possible? Absolutely. So 0 is a legitimate value, but negative is not. And so if I try to give it a negative value, I'm going to throw an exception. Okay, so now I have 2 sensors that we can play with. Now let's look at what else. Okay, so now the minimum thing to get the enter and range is our simplest referee. So it's going to be responsible for scheduling the enter range and exit range events. It has 2 parameters. One, it has a simplest mover, which is going to be the target. This is going to be the target. And a sensor, which is going to be a simplest abstract sensor, meaning that I'm going to specify the type as a simplest abstract sensor because I want to be able to see right now I have a simplest cookie cutter sensor and a simplest constant time sensor, but they're both subclasses of the simplest abstract sensor. And so if I declare my type of sensor to be the simplest abstract sensor, that means I can put either one of these in. If I were to say, the alternative would be to have one referee for cookie cutters and another referee for constant time and another one for the constant rate ones and another one for any other type of sensor that I might want to come up with. Rather, all I need is that a sensor to use be a subclass of the simplest abstract sensor, and then it's good. So it's going to listen for the start move and end moves from the mover, and it's going to listen to the start sensor move and start sensor end move from the sensor. And then the enter and exit times event, there's an event I called enter exit times. And what it's going to do is it's going to compute the solution to that quadratic equation. Sometimes the PowerPoint autocorrect is a little aggressive. Okay, then it schedules an enter range of 2 positive roots. It schedules an exit range of 1 positive, 1 negative root. And we've seen the methodology behind that, but let's look at the implementation. Okay, so this is our simplest referee. You see all of these are in a package called mv3302.sensor. So we're a sim entity base. We have 2 state variable, we have 2 parameters. We have no state variables. So here's our simplest mover target. Our simplest abstract sensor is we'll call a sensor. And now we have, okay, so we have a 0 argument constructor. We have a master constructor with all the parameters. And so we're going to call this and then set the target in the sensor. Now, just as we did for the simplest abstract sensor and it's listening to its mover, now we want to make sure that the referee is listening to both the sensor and to the target so that when we set it, we're going to add it as a sim event listener. Again, this is this is the simplest one. In the more complicated ones, we need to be just a little bit more careful. But for this simple one, That's kind of good enough. All right, so let's look at our events. Okay, so here the event graph looks a little bit complicated, but here's the thing. So here's our sensor and our mover, and we're listening to both of those, and we're listening for the start move and end move events, and start sensor move and end sensor move events there. And now the enter and exit times are going to be where we compute the root. So if the roots are real, and one is TL is the lower root, TU is the larger root, smaller, maybe it should be TS and TL, but TL for lower, TU for upper. And so if they're real and positive, if they're both positive, then the enter and exit times is going to schedule an enter range event passing both the target and the sensor. And the condition for that is that we have two positive roots. However, if we are inside the range, then we will schedule an exit range, and that will happen if the lower root is negative and the upper root is positive. And then as it turns out, and again, the delays are going to be the respective roots that we have there. And then as it turns out that since there may be, when implementing this, it turns out that we can have multiple enter and exit times. So whenever that occurs, we want to sort of interrupt any pending ones, so we don't have it multiple times. All right, so let's look at how that works. Okay, so we're back at our simplest referee. So our start move event, okay, we're going to hear that from our target, and it's going to schedule the enter, I call it schedule enter exit. And likewise, an end move is going to do the same thing, and a start sensor move and an end sensor move. Notice that I've given them low priorities because I want to make sure that if at the same time there's any other changes in their movement to take place, then I want to do these calculations after that. Otherwise, I'll just have to keep spinning. Okay. So let's look at that. So first of all, we interrupt. That's what this canceling edge was about. And okay, so here's what I'm doing in this. I'm first determining the distance between the target and the sensor. And if our distance is bigger than the max range, then that means that there might be an enter range event that's already been scheduled. So I want to cancel that. On the other hand, if we're inside of the max range, then it may be that there's an exit range that had been scheduled and the mover has changed its direction. So we want to interrupt that. We want to cancel any of these pending enter range or exit range events because a start move or an end move on any of their parts has indicated that the relative position and velocity of the target and the sensor has changed. And so any previous pending enter or exit events that are on the event list need to be removed. Okay, now just for convenience, I've defined just one method. There's a method that's going to get these times. And so I've kind of shoved all that calculation into another method, which we'll take a look at in a moment. And that's going to return either an array of length 2 or an array of length 0. Or sometimes it returns an array of length 1. So it kind of depends. but I'm only interested in the number of roots that's 0. So if the roots are complex, then it's 0. So if I have 2 roots, then here's where I check. If it assumes that the lower root is the first one, and if that's bigger than or equal to 0, I can schedule an enter range with that delay passing the target and the sensor. On the other hand, if it's less than 0 and the larger root is bigger than 0, then I can schedule an exit range, again, passing the target and the sensor. So what I need to do is find so here's the enter and exit. Here's where I do that calculation. And now I have two choices. One is I could implement all those square root business before, or I can take a slightly lazier way out and use something that's built into Java. So that's what I'm going to do. So here my times are going to be okay, we'll start with an array of 2, and then I'll override it if we kind of miss. So first I need to compute the relative location. So remember, that was the difference of the 2 vectors, the x location of the target. So this is the x coordinate of the target minus the x coordinate of the sensor, the y coordinate of the target minus the y coordinate of the sensor. That's the relative location. The relative velocity is going to be the x location of the target's velocity minus the x location of the sensor's velocity, and the y coordinate is going to be the y coordinate of the target's velocity minus the y coordinate of the sensor's velocity. So now what the Java method I'm going to invoke is, there's something called a quad curve 2D that has a method called solve quadratic. And what I do is I give the coefficients of the quadratic equation, and it will put the roots into the times here. And what it returns is it returns how many roots there are. So here's where I put the coefficients in. So the 0 coefficient is the square of the relative distance minus the square of the maximum range. The middle one is twice the relative location times the inner product, and that's what that is. And finally, the coefficient of t squared is the square of the relative velocity. So then I just call solve quadratic. It gives me the times, and then just to make sure they're in the right order, I sort them. So that makes sure that the smaller root is the first one and the larger root is the second one. And then what I'm going to return is, if I have 2 roots, I'm just going to return that array, and otherwise I'm going to return an array of length 0. And that will allow me to say, I can double check the number of roots here. That's going to be the length. It's going to be either 0 or 2. Okay, so now let's fire this baby up. So here's how we do that. Okay, I have a number of different tests here but first we're just going to, let's see, first we're just going to look at the referee here. So here, let's set up the sensor. So the sensor needs a mover, and my mover is this. The sensor is going to be at 15.0, and in this case, it's going to be stationary. So I'm going to give it actually a maximum speed of 0. That's legitimate. And so my sensor is going to have that mover, and it's going to have a maximum range of 50. And I'll print that out both the mover and the sensor just to make sure that they're working. I do the param string thing because the sensor, for the sensor, it's 2-string, also needs to know where it is, etc. So, okay, so here's my target. It's going to be a simplest mover as well. And so I'm going to put it at 60/80 and give it a speed of 20. Okay, so there's my target. So for my target, I'm going to give it a path mover manager. And I'm going to give it a bunch of waypoints. So first I'm going to go to the -1. That's going to ensure that I actually pass through the sensor's range. And then I'm actually going to go back to my starting place. Then I'm going to go and stop somewhere inside of the sensor and then start again and move outside. Okay, so this should give me an idea of kind of what it's like to maneuver once I'm inside the sensor's range. Okay, so my simplest path mover manager, that just has the path that's true. And then as we have done, I need to have it listening to the target and the target listening to it. And we'll print that just to do that. Simple property dumper, our old friend. Okay, so we want to listen to the sensor. Probably want to listen, well, the sensor is really the important one. Okay, so here's our simplest referee. So I give it my target, I give it my sensor. And again, I'm just listening now for that, and I'll print it out just to see what it is. We'll go verbose. We're going to reset and start our simulation. Now here I've actually, since we haven't talked about the mediators yet, I've commented that out. But let's see what happens when we run this. And hopefully it still works. All right, let's look at. Okay, so our first simplest mover, that's for our sensor. Sorry. Cat. Okay, our sensor located at max speed of 0. That's okay. So here's our cookie cutter sensor, and says it uses the 2-string when it lists its parameters, and the 2-string for simplest mover just kind of gives a not an NAN because it hasn't hit reset yet. Max range of 50. So here's our target. Its initial location is at 60 minus 60/80, and the max speed is 20. And that's because I'm printing the param string for these. Okay, here's our simplest path mover manager. Here's our path that matches. We're going to start on run. And then here's our referee. Again, it's going to list our everything is not a number because we haven't reset yet. So now we have a sequence of run events. So here's run. Here's the simplest cookie cutter sensor. It's run fires a property change for contacts. Contacts are empty. Okay, check. Then this is our target. And then here's our simplest path mover manager. What we really should do is we should just let's start again, just so we get everything here. All right, so okay, there are our contacts. There are our okay, so here our simplest mover. This is the target. Start move time 0. Last stop location initial Its destination is not a number because this is just the run event and its velocity is 0. Okay, fine. And here's our simplest path mover manager. Its run says our next index, our next waypoint is not a number, but it schedules our next waypoint. So, okay, so all that's working, hopefully. So then our next index goes from -1 to 1. Our next waypoint minus 60 to -80. Schedules the move to. That sets the destination. Move to schedules the start move for the simplest mover. Again, start move times 0. Velocity now becomes -12, -16. And now, okay, so now the simplest referee has heard that start move, and so it's going to schedule the enter and exit. And as a result, it is scheduling the enter range at time 2.1231. And so there the exit range, enter range occurs, and enter range schedules exit range at this time. Okay, so exit range happens, and then sometime later we have the end move. Then the end move is going to next go to our next waypoint, schedule, et cetera, et cetera. So it's going to double back. And then once we start move, okay, now here's when, remember I said that it had to cancel because sometimes we get 2 of these on. All right, so notice when this happened, it canceled the other one, and then it scheduled the enter range again. So it's, and I see that we are now finished here. And so this will be continued tomorrow.